Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the SwayamPrabha course titled Maritime Structures Under Fire, Blast and Explosion, coordinated by myself, Chandrasekaran, and then Professor Srinivasan of Civil Department. This is a course under the program of Masters in Maritime Engineering. So this particular course has got lot of industry driven contents which are very important for employability and also for advanced research facilities as applicable to maritime industry. Let us talk about the explosion as a sequel series of the lecture to learn more about the details of explosions, fire and blast loads in this lecture. So friends, welcome to lecture 11, explosion sequel lecture. Let us quickly see what we have learned so far in the previous lectures of fire characteristics. We understood that fire continues to exist, still there is energy. There are two ways fire can be extinguished. Fire, if it is fuel controlled, It will keep on burning until fuel exists. If it is ventilation control, then one can also again alter the fire characteristics by altering the ventilation effects in the given system. Usually in hydrocarbon fire, which is likely to happen in maritime structures and heavy industrial structures, usually and mostly they are fuel controlled, except there is a compartmental fire where there is a ventilation control possibility. So, under fuel control fire, fire will continue to grow and stay in a steady position until there is energy continue to be supplied to the system by the flammable materials. When we talk about classification of these fire resulting in explosion, then pool fire, jet fire, flash fire are considered to be one of the dangerous scenarios in industrial structures. However, when we talk about impact of these explosions on structural systems, BLEVE is the most impulsive high energy explosion which happens with a maximum potential and have a high risk to cause damage to the structural systems. So, BLEVE, we have already seen the consequences and the causes and reasons for BLEVE, and how to mitigate the effects caused by BLEVE is also understood by us in the last lecture. We have also seen there are 3 design parameters to compute different categories of fire based on burning, which has been discussed in the early lectures. So, now we understand further that on hydrocarbon fire on top side, let us say CNG platforms or LNG storage gasification units, explosion has deadly effects on the maritime structures. It has got a very high risk which is caused due to explosion, and it can result in unpredictable losses. Friends, risk can be easily computed as a product of frequency of occurrence and consequence. Because of the accidents being very rare in hydrocarbon sector, the frequency can be not very often, but even if it happens once in a year, let us say, for example, as a count, the consequences caused by these are very large. Therefore, any fire or explosion accident is always accorded to as an event of very high risk. So, risk is very high in terms of explosions, especially when it comes to BLEVE, and they can result in unpredictable losses. So, friends, it is important for us to learn the mathematical modeling, the parameters that govern these kind of accidents, and also understand the mitigation effects, so that the consequences caused by this can be reduced. You cannot avoid these because they are actually accidents which are likely to happen because of various reasons which are beyond the control of human factors. But however, when such accidents occur, we can always look into the fact that there is no repetition of such accidents occurring because of human fault. Of course, mechanical, electrical faults are not in the purview of human control, but however, we should ensure that these kind of accidents are not repetitive, and if at all they occur, we will try to mitigate them in terms of reducing the consequences caused by these accidents, so that the effect of risk is minimized on maritime structures. Having said this, let us try to learn more about explosion in this lecture. As we said, explosion is a rapid expansion in volume resulting in outward release of energy at high temperature and pressure. Irrespective of type of structure, all structures suffer potential threats from explosion. We can straight away say this, not necessarily only maritime structures, because explosions can cause from any medium as liquid, gas, and even dust. Industrial structures often have problems of heat being supplied to the source of flammable stock or inventory areas. At the same time, the fire rescue plans or explosion prevention systems may not be effectively in place. Therefore, not necessarily type of structure as applicable to, irrespective of its type, all structural systems, in fact heavy industrial units, we can say heavy industrial structures will suffer risk due to explosion. Okay. So, we are saying that irrespective of type of structure, all structural systems will have a potential threat from explosions. So, the design of fire, blast and explosion loads are not definitely constrained only to maritime industry. Even heavy industrial structures, process industries, paint, chemical, manufacturing industries, cement plants, fertilizer plants, all are subjected to these kind of explosion probabilities, because they all anyway handle flammable mixtures or chemicals. It can be in any form of liquid, solid or even dust. Therefore, friends, understanding the process of explosion helps the designers to understand and implement various design practices that can effectively address the consequence of explosion. That is a highlighted point here. We are not addressing the causes caused by due to explosion or arising or reasoning to explosion. Our focus is to reduce the mitigation effects and to reduce the consequences caused by the explosions. As we all know, when a vessel containing pressurized gas ruptures, the stored energy in the pressurized vessel at a very high value is released, and unfortunately this release happens instantaneously and suddenly. If the contents are flammable, and then the ignition of the released gas could cause more consequences. Supersonic explosions and subsonic explosions are referred to as detonations and deflagrations respectively. Supersonic explosions occur when they travel through shock waves. Subsonic explosions occur by low explosives, and the process is slightly slower in combustion compared to supersonic. That is why the name supersonic and subsonic related to the spread of the shock wave, because this is faster, this is slower. So, one is referred as detonation, another is called as deflagration. Chemical explosives are most common artificial explosives. They involve rapid and violent oxidation reactions, and they do produce lot of hot gases. Such explosions usually occurs in fuel tanks. Every heavy industry always have an inventory of stocking fuel which is inevitably required for the process. Especially hydrocarbon industries, where they are handling process of hydrocarbon itself, they are highly vulnerable because they are dealing with flammable liquids every day and then. So, explosions usually occur when you have got fuel tanks in place, when there is a probability of electric spark being initiated. In the presence of ambient oxygen, it catches fire and depends upon the instantaneous release of pressurized gas or flammable material, can become explosion. So, there is no much difference in the process between a fire and explosion. In simple terms, if I have a pressurized vessel, which comes in contact with heat, or there is a source of fire, it expands. And if it happens to be a flammable mixture, the release of this mixture suddenly can cause fire, can also result in explosion. It all depends upon what is the quantity and what is the fuel air mixture available. The fuel air mixture availability there in the vessel decides whether it is going to cause fire or it can result in explosion. So, the process is actually a continuum of what is happening after the release. So, now one can ask me a question, how we can use preventive measures to control explosions. Now, if you look at the heavy industry like hydrocarbon industry or even maritime industries where lot of inventories of gas is being handled, there is no possibility of avoiding electric spark because we carry out lot of heat operations like welding, grinding, etc. So, electric spark is inevitable, and we generally have a workspace where there is abundance of oxygen available. Looking at the fire triangle, fuel is anyway present in the fuel tank, you have heat source or sink available and you have oxygen in abundance. So, there is going to be fire for sure. It all depends upon what is the pressure at which the flammable chemical is handled and how it is being released, and how the ignition after release is delayed or if it is instantaneous. So, that causes explosion. Therefore, friends, explosion is influenced by many parameters. One is the ambient temperature and pressure at which you are working. So, that is why generally you see in most of the workspaces in industrial structures, the work platform is always open and lot of ambience is allowed to permit, so that the temperature and pressure remains under control and normal. No extensive heat, no extensive cold. Second factor which governs explosion is the composition of explosive material. As I said, the fuel air mixture, the composition and its physical properties. In the last lecture we discussed about two important properties of the mixture, what we call as flammable limits upper flammable limit and the lower flammable limit. If the fuel air mixture is above UFL or below LFL, no issue. If it is within this range, then it catches definitely fire and the combustion can also result in explosion. So, the physical properties and the composition of the mixture can result in explosion. The third factor which governs explosion, which is most important, is the nature of the ignition source. Is it instantaneous or delayed? Is it at high temperature or ambient temperature for a long sustained period, and so on? What is the nature? And importantly, the duration. How long will supply source of heat to the fuel? The next important factor which also governs explosion is the amount and turbulence of the material. As I said, one of the important governing factor which helps us as a designer to control or mitigate explosion causes is the time before ignition. You can always delay the time of ignition by some process by which can reduce the consequence of explosion. So, time before ignition is a very important parameter which governs the consequence of explosion. And above all, we know that release rate of material, what otherwise we call as heat release rate. So, the release rate of material also governs the explosion nature and the consequence of explosion. So, factors govern explosions are temperature and pressure, composition, nature and duration of ignition source, amount and turbulence of explosive material, time delayed for ignition and the release rate of explosive material. If they are instantaneous, it may even cause a fireball or a blaze. If they are continuous process at a specific constant rate of release, it may not, it may become even a flume and so on. So, friends, explosion caused by pressure waves which propagate in air. So, explosion essentially moves forward in air in the form of waves. These are called as pressure waves. These are also known as blast waves, which is followed by a strong wind. So, the windward action is one of the supporting factor for improving the consequences of explosion. So, explosion is caused by a pressure wave referred as blast waves in the literature. Shock front is expected from highly explosive material like TNT. TNT is one of the referral material of explosion which we use in literature to compute the consequence of explosion caused by any flammable material. So, if you have any flammable material available, we will always try to find out TNT equivalence of that material, whereas TNT is referred to as a very standard referent material of explosion. A shock wave is expected to move forward with highly explosive material, which generally occurs when there is a sudden rupture of a pressure vessel. When there is a sudden rupture, it generates maximum pressure, and this pressure goes much above the ambient pressure, and that is termed as peak overpressure P naught. The blast wave pressure developed in the propagation direction is also termed as side on overpressure. It is also referred as free field overpressure. So, friends, in simple terms, when there is a container which is under pressure holding large quantity of flammable material and fractures or ruptures because of some corrosion problem or because of some connection difficulties, a shock front is developed which releases equivalent amount of TNT. This follows by blast waves which is supported by strong wind in the windward direction. The shock front also grows as a peak overpressure, and the blast wave pressure also grows as a free field overpressure. So, if it is measured facing the incoming shock waves, then it is called reflected overpressure. For example, I have a container, let us say a capsule or a bullet, which is containing flammable liquid or flammable gas inside, let us say. Okay. It is placed very close to the heat source. The heat source can be even not necessarily a flammable light, can be even an electric spark. Okay. I am just indicating this as a schematic diagram. So, what happens if this flammable chemical will expand and it increases pressure? This overall pressure will exceed the capacity of the vessel. When it exceeds, then the vessel ruptures. When the vessel ruptures, it releases the chemical. Okay, and this now causes fire or explosion. So, if it is measured in the direction of incoming shock waves, for example, there is a shock wave which is travelling, and you measure this in the direction of incoming shock waves, then we call as reflected overpressure. Usually, reflected overpressure is twice in magnitude of side overpressure, usually. But in certain cases, the reflected pressure can be even as high as 8 times of side overpressure. Explosions result in a blast or a pressure wave moving out from explosion center, and they move at a speed of sound. That is why generally we categorize them as supersonic or subsonic related to sound. Shock waves or overpressure is a basic cause for the damage. The damage is essentially because of the shock wave. Projectiles are other important source of damage, because when the vessel blasts, the piece of vessels start flying, moving in all directions. These are called as projectiles, and they also cause damage. Therefore, friends, damage is now a function of rate of pressure, and depending upon the rate of pressure increase and duration of the blast wave, damage can be higher or lower. Blast damage are estimated based on peak side on overpressure. Explosion of course generates a rapid rise in pressure. As the shock wave propagates, it is followed also by a negative pressure wave which causes further damage. Let us look at a graphic representation of this in the next slide. Friends, look at this figure which explains the pressure trajectory over time, the pressure history. Let us say a pressure is released at an ambient condition, and after a specific delay of arrival and the pressure shoots up to a very high value, we call as peak overpressure. Once the peak overpressure is reached and the flammable chemical is released because the vessel is ruptured, then the pressure drops. But interestingly friends, it drops below the ambient level and causes a suction or a negative pressure. This is the most dangerous part in the consequence of explosion. This negative pressure causes lot of side effects on buildings, structures, equipments and even human. And once it has got a time duration of negative pressure happening, then it returns to the normal pressure once the fuel is completely exploded. So, peak overpressure governs the maximum pressure at which explosion can take place. So, figure shows the variation of peak overpressure with time. The area under this curve, without neglecting the negative one, is a measure of severity of explosion. The area under this curve will give you the severity of explosion. As seen in the figure, an explosion generates a rapid rise in pressure, while the propagating waves cause damage to the objects located on its path. It is then followed by a negative pressure, which causes further damage before pressure returns to atmospheric value. Therefore, friends, damage depends on the maximum overpressure, the velocity of propagation and environmental factors. Environmental factors could be wind, that is wind speed, wind direction, etc. Then other could be humidity, then other could be the ambient temperature and pressure, and also other factors like topographical effects, because any obstruction to wind flow will cause return overpressure, which again imposes further damage to the structure. So, topographical effects can also be considered as one of the factors here. So, I can write here topographical effects, what we call as terrain effects. Okay. In many of the cases you might have noticed, even after the explosion stopped, still damages are continuing. Okay. That is because of the terrain effects happening. So, friends, explosion damage, as I said, is actually worked out in the form of TNT equivalence method. The question comes, what is TNT? TNT is abbreviated as trinitrotoluene, which is a very important explosive referred in the literature. The chemical formula for TNT is what you see here, and it decomposes as nitrogen, carbon dioxide and steam in the form of gas, and this remains as a carbon powder we call this as a soot. This is a thick black carbon powder which becomes an byproduct after TNT is burnt. So, what is specialty about TNT? TNT is an explosive which can quickly change its composition from solid to expanding gases. That is the beauty with this chemical. So, it can quickly change its form from solid to gaseous state. So, when you heat this, it becomes gas completely, and of course, it leaves a black powder, a residual powder called as soot. So, TNT is an explosive for two different reasons. It contains elements of carbon, oxygen and nitrogen, as you see here. Carbon, oxygen, nitrogen. So, it is definitely an explosive, which means that when it burns, it produces high stable substance which has got a very strong bond. That is one first reason why TNT is accorded as an explosive. The second reason is TNT explosions are chemically unstable, which means that it does not require much external force to break this bond, though they form a strong bond, but it can be weakened easily without putting much effort or much external force to it. So, TNT quickly forms, burns faster and develops stable substance, and that bond between the substance can be easily broken with less amount of force. So, for these two reasons, TNT is always considered as an explosive, and all damages caused by explosions are always computed in terms of TNT equivalence. We will see that in the coming lectures. Furthermore, friends, you must have noticed there is something called plastic explosion. It comprises of RDX. It is actually a mixture of oil and plastic resin which has more severe consequence in terms of damage, in terms of impact, in terms of velocity of propagation compared to TNT. It is otherwise referred to as plastic explosion in the literature. So, these are all different forms of explosions available in the literature, and whatever explosives we have in the form of hydrocarbons, instead of reading them, studying them independently, we convert them into equivalent amount of TNT because the damage caused by TNT is well known in the literature, is established. Therefore, if I am able to find out what is the equivalent amount of TNT available, then I will be able to correlate that with the extent of damage. For example, in case of fire, you have any product which is actually combustible, but we try to find out equivalency of wood in terms of fire, in terms of calorific value. So, what is the equivalent, wood equivalent of that calorific value? Because you know how much time it takes for wood to burn and the consequences if it burns, it is all well established in the experiments. Therefore, any new kind of cellulose fiber, any new kind of chemical or substance which catches fire, if you want to compute the consequence of that, the best method is to find out the wood equivalent of that, so that you can always correlate the damage compared to that of equivalent amount of wood. So, TNT is an established explosive which is very stable compound when it burns very quickly, and also it becomes a weak system to break up in case of chemically instability. Having said this, let us look at what is the effect of the explosion force in the ambient condition. The explosion force is generally released in direction normal to the surface of explosive. If an explosive released from a specific surface, energy is released in a direction perpendicular to that surface. But if the explosive is released in mid-air, then the direction of the blast will be around that 360 degrees. Okay? If it is from a specific container released then it will be normal to the container. If it is released in air, then the release is affecting full 360 degrees. The next question comes, speed of an explosive reaction. The speed of an explosive reaction is very rapid, is very fast. It is an outcome of thermal expansion of gases causing high pressure and heat. There is a rapid liberation of heat which causes instantaneous expansion of gases, and that generates very high pressure causing explosion. A substance that burns less rapidly is referred to as slow combustion. The one which heats faster is fast combustion. Slow combustion converts more of the internal energy of burning substance into heat and it releases only heat to the surroundings, whereas fast combustion converts the internal energy into work and it spreads on the surroundings. This work is actually the impact force or the energy. So, therefore, friends, when we talk about hydrocarbons, talk about LNG, CNG platforms, processing units or any bottling units, etc., which are on the offshore structure or on the port and harbour structures for inventory stock, they are highly explosives because they deal with fast combustions and they release energy on the surroundings which can cause severe impact to the buildings, structures and human. So, when you have got a contained vessel which is under pressure, if the pressure exceeds its capacity, it ruptures. When it ruptures, it causes explosion, and that can occur due to the following reasons. One, there can be a failure of the pressure regulator valve, because every vessel has got something called pressure release valve or pressure regulatory valve. Okay, it is for a safety purpose. For example, even if you have a cooking gas and you are using a steam cooker to boil vegetables, etc., at home, there is always something called a safety valve. Okay. When the pressure in the contained vessel increases capacity beyond its capacity, the safety valve releases the excessive steam so that the pressure inside the vessel is contained, it does not exceed. If you do not have a safety valve properly fixed, then it can rupture. Okay. There are accidents at homes where the steam cooker also ruptures when there is a defective safety valve present in that. Similar to that, in industrial units we have something called pressure regulators. There are also pressure relief components available which are fixed on the system. So, if they fail, it can cause rupture. Secondly, there can be reduction in the vessel thickness. That can happen when there is a corrosion present. Hydrocarbons are highly corrosive as well. So, the corrosion degrades metal strength, it decreases the thickness of the vessel, so the vessel can rupture. Thirdly, if you are stocking any chemical or it passes through a chemical line intensified, can also cause erosion. Furthermore, friends, when you got a pressurized vessel contacted with heat source, excessive heating can also reduce the strength of the vessel. You know, we already seen any metal like steel under high temperature loses its strength. Okay, we already seen that in different courses, and you have an idea that there is a strength reduction of steel when there is overheating. So, when the heat source is very close to the pressurized vessel, there is a continuous supply of heat source, it can reduce the vessel strength. Furthermore, friends, the vessel may be subject to chemical attack, can also then cause rupture. If the vessel is under fatigue induced weakening, which can happen because of reversal of pressure, like ballast chambers, or ballast tanks. I mean, please note, this is not blast tanks, this is ballast. Ballast actually is a tank where people stock water or any other material for improving the weight. Okay? These are very usually applied on floating structures or floating vessels. Example could be a drill ship. So, ballast tanks, they will be frequently loaded, offloaded by the ballasting waters, what we call ballasting, deballasting. So, this can induce fatigue induced weakening or fatigue induced cracking. This can also cause rupture. Sometimes there can be internal runaway reaction because of the chemical action happening within the flammable material. This can also cause rupture. So, rupture of the pressurized vessel can happen under various reasons. Having said this, let us quickly look at the amount of energy released during explosion. The amount of energy release depends on vessel stretching or tearing, kinetic energy of the fragment, and energy in the shock wave or a waste energy released in surrounding air. The major human effects caused by fire and explosion is summarized in the table which I am showing in the next slide. Studies show that overpressure resulted from explosion is not significant in open areas. So, that is why friends, many of the industrial sector units have their workspace mostly uncovered or mostly unconfined. But a complex geometric layout of the plant or an offshore drilling deck can initiate high explosion over pressure. So, all the time open surrounding is not favorable, can also sometimes cause high explosion over pressure. Let us now see what are the major human effects caused by explosion. Let us say it can result in eardrum injury. The damage can be eardrum rupture, which is a direct effect from overpressure. There can be probability of death due to lung damage. The explosion can cause sudden pressure difference between inside and outside of the lungs, due to which fatal result can occur. There can be probability of death from head impact. Shock waves can push head of a person backwards, resulting from skull rupture or fracture of the spinal cord. Sometimes it can even cause collision of heads with other stationary objects. You must have seen in many places, especially in road accidents, you must have seen the head crashes with the dashboard and the spinal cord breaks and people die. There is also a probability of death due to whole body displacement. Shock waves can throw the whole body backwards and forward, causing death because of its impact with other objects. Therefore, friends, explosion in maritime industry, shipbuilding and offshore platforms can lead to severe consequences. Many studies showed that as much as 2/3 of losses arising from an accident are due to explosions. That is a very interesting factor which we must learn and appreciate. More than 60% of the losses occurring from explosion in industries. More than 3/4 involve explosive material, that is another deal. In a general statistics, it is reported that 18% fire are due to release of flammable gases. Therefore, friends, in the total loss of accidents, fire contributes about 20%, which occurs from explosions. So, therefore, let us look at the general statistics of accidents and the summary. Fire and explosion accidents in maritime industry arise from 4 sources. Human error is close to about 50%, mechanical fault 22%, thermal reaction 14%, electric fault 7%. So, friends, if you put all the mechanical and electrical components together, human error plays almost equal role in causing accidents. Okay. So, therefore, we generally tell or advocate that a strong training towards safety and a good capacity building towards understanding fire and explosion is essential, because at least we could avoid human errors. So, whatever errors come from equipments, plants and thermal reactions, if we leave them apart, for example, let us say we have no control over them, even then straight away the mitigation effects can reduce to 50% if you avoid human errors. Okay. The major factors that contribute to fire and explosion due to human error are poor maintenance scheduling, inadequate training and education, and lack of awareness of the situation. Factors contribute mechanical faults could be maintenance works in error, metal fatigue, excess heat generation, and faulty operational conditions. Short circuits can happen from poor connections and maintenance problem, or use of defective devices, which all together can result in fire and explosion. So, friends, let us look at the summary of this lecture. In this lecture, we learnt about explosions more in detail. We understood that TNT is the standard referent material of explosion, which is considered as an important reference to compare the damage caused by explosions. So, it is a standard reference material for two reasons. Okay? It can expand fast and it can form a stable compound, and the bonding can be loosened very quickly without much effort. We also saw what is RDX in detail about the plastic explosive. So, these are all actually reference materials used. So, when you have got any flammable chemical which can cause explosion, then to find the effect of this explosion, we always try to find out TNT equivalence to get the effect of explosion. So, we convert the explosives into equivalent TNT to get the effective of explosions, which we will look with design examples in the next lecture or looking forward. So, we said what are the factors that can cause fire and explosion, and we understood that in all these accidents in general, based upon the statistics available in the literature, about 50% is from human error, and it occurs due to improper training, lack of education, lack of safety practices implemented in place. Rest 50%, even though they come from mechanical, electrical faults, if you take them as unavoidable for 1 minute, still one can reduce the consequences of accidents if you are able to do a proper capacity building in the human. So, that is the target of this lecture. So, friends, hope you have understood this lecture thoroughly and you will be following the sequel of explosion lectures in this course, and should you have any doubt, please post them to the email ID given in SwayamPrabha course, and the instructors will be able to get back to you with more details and explanations. And I will always request you to look back the reference materials suggested by us and have a copy of them for your institute library and read them for reinforcing your learning again and again. Thank you very much. Namaste.